title of these slides are Taylor Polynomials. It's actually more of a quick introduction into series, though I do start with Taylor Polynomials to kind of motivate why I'm doing this. So first off, the idea with Taylor Polynomials, wouldn't it be great if we could rewrite all of our functions as polynomials? Because they're so easy to take the derivative of, they're so easy to integrate, not so easy to factor sometimes. So let's look at this. So let's say we have a function, and I'm going to write it as this polynomial, an infinitely long polynomial, possibly, but a polynomial. I've got a sub naught as a constant term, a1 is the coefficient of x to the 1, yada yada yada, and a sub n is the coefficient of x to the n. And I'm going to plug in 0 because I want to figure out what these a's are. So if I plug in 0, f of 0, all these other terms go away, so my first term is a naught, or a sub 0. Okay. Now, I need to figure out what a1 is. Well, to get it by itself, I'm going to take the derivative of f of x. So if I take, oops, too far. If I take the derivative of f of x, the first term goes away. I'm left with a1, blah, 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 all this stuff. Notice the 2 comes out front. Here the 3 came out front, and then the 4 came out front all the way down the line. If I plug in 0 now, I get f prime of 0 is a1, or really a1 is f prime of 0. So, because I want to get a formula for the a sub n's, or a sub k's. So let's take the derivative again. This time, notice my 2 is now at front, because I had x, this had started as x squared. So first the 2 came down, then the 1 came down, so I've got 2 times a naught, and all these other things have x's attached to them. So when I plug in 0, everything goes away but this first term. But I do want you to notice what's happening. This was the x cubed term, and it's going to be marching toward the front. And as it marches toward the front, each power is going to come out front. It had a 3, it had a 2, it's going to have a 1 next time. Here, the fifth one, it started with a 5, then a 4, and then it's going to have a 3 and a 2 and a 1. So we're going to have a factorial going on here. Okay, so let's look at this first. So I've got put 0 into the second derivative. Solving for a sub 2, I get the second derivative with 0 plugged in divided by 2. The only difference is when we start solving for a sub 5, we're going to get a5 equals the fifth derivative with 0 stuck into it over 5 factorial. Because by the time it gets to the front, you'll have all those terms multiplied together. So my formula for a Taylor polynomial will be this. The summation as n goes from 0 to infinity of the nth derivative with 0 plugged in over n factorial times x. Now, we know that this is true at 0, but that doesn't do me much good because we plugged it in. We forced it to be true at 0. I kind of want to know what interval it's true on. Like it's true at 0, but is it true at 0.5? Is it true at point negative 5? Point negative 5? That doesn't make sense. Negative 0.5. So we worked on that more in the next video. This one I want to talk about how do you know when a series converges or diverges. And to do that, we need to back up and remind ourselves what a sequence is and then talk about a series. So a sequence is a list of ordered numbers, an ordered list of numbers. I'm a little dyslexic here. And the series just means you add them up. We want to know whether they add up to a number or they go off to infinity. So we say converge or diverge or neither. So we're going to start with looking at some basics. If the terms themselves do not go to 0, the series must diverge. Remember that. The terms don't go to 0, you're screwed. The series diverges. You can't add up something bigger than 0 or smaller than 0 infinitely many times and get a number that's not infinity. Our question that we ask ourselves, though, is does a sub n go to 0 fast enough? Now, one thing you might want to do is review when a sequence converges or diverges in terms of comparing it to functions. And if you go back, I have a video on that looking at to infinity and beyond or something. You know, when do sequences or series, when do sequences converge? So let's keep going. So what kind of series do we have? First off, we're going to look at the geometric series. A geometric series will converge only if the absolute value of the ratio is less than 1. I don't care if it's negative 1/2 or negative 1/3 or positive 1/3. As long as the absolute value is less than 1, then the series will converge. Now, This is the basic generic way to write a series. And if you think about it, you've got some first term, and then each time you multiply by your r. I want to find the sum of this series, because this is one we can actually find. It's not too bad. So to do this, we're going to look at partial sums. We're going to say S sub n is the first n term. So we've got ar squared, blah, 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 up to a times r to the n minus 1. Take this expression, multiply through by r. So that takes all of these and shifts them over by 1. So each one we start with ar squared, all the way up. This last one was a sub ar to the n. Now notice how these match up. If we subtract one equation from the other, that whole chunk of terms will go away, and we're left with S sub n minus r S sub n is a minus a r to the n. Now, what I care about is what S sub n is. So I'm going to solve this equation, factor some stuff out, divide, where'd it go? Divide, and solve. Now, this is the partial sum at when you do the first n terms, but what happens as n goes to infinity? Well, since the absolute value of r is less than 1, r to the n as n goes to infinity is heading to 0. So this term is going to go away. So the limit of S sub n as n goes to infinity is just plain old a over 1 minus r. The key here is what you want to remember is it's the first term in your sequence or series over 1 minus r. So let's look at a couple of examples. So here is a geometric series. First term is 3, then 2, then 4/3. Each time I'm multiplying by 2/3. That's my ratio. So my formula says I want the first term on top, so I want 3 on top, over 1 minus the ratio, and the ratio is 2/3. So I have 3 over 1 minus 2/3, which gives me 9. Let's try another one. Here I have, oh grossness, n goes from 0 to infinity. I really don't care where it starts. That's just going to tell me what that a is at the beginning. But so let's look at this. We have 4. Okay, that's just a number. It's not raised to a power. I could suck it out here. No harm, no foul. 2 to the n, 5 to the n. That means each term is being multiplied by another 2/5. So my first term, let's plug 0 in. So I'll have 4 will be my first term. And the ratio is 2/5. So 4 over 1 minus 2/5. So simplifying the fraction, I get 20/3. So that is the sum of that geometric series. Let's try another one. This looks much grosser, but take it one step at a time. My ratio is still 2/5. Even though they're little cattywampus, this one's off by 1. It doesn't matter. Each term is going to get an additional 2/5 multiplied. So I'm going to have 1 minus 2/5 on the bottom again. In the numerator, I need to figure out what the first term is. And I noticed that n is equal to 2. So that was kind of a bitchy move on my part, but that's okay. Let's try it. Let's plug it in. So if n equals 2, I have 2 squared is 4. I've got 16 on top. Down here, I have a plain old 5. So the first term is the top is 16 and the bottom is 5. I forgot I stuck that in there. So when I do the formula, I get 16/5 over 1 minus 2/5, which when you simplify, you get 16/3. So just if you remember that the sum is just whatever the first term is over 1 minus the r, it makes your life a lot easier than trying to go, oh, well, if this is n is k, and blah, blah, and you know, you could learn 4 or 5 different formulas, but that's the only one you need. Now, this is one I want to kind of prime the pump for. Notice if I have x to the n, my first term is 1 and my ratio is x. So this is kind of hinting toward what we're going to be doing with Taylor series. This function can be written by this infinite polynomial. Okay. So let's look at the other type of series we like to play with are called p-series. And a p-series will converge if and only if your p is greater than 1. This is what it looks like. We say n starts at 1 because you can't put 0 on the bottom. World explodes. So why is this true? Well, go back and remember when you did improper integrals. We looked at y equals 1 over x, and we integrated from 1, supposed to be 1 there, 1 to infinity, and we found the area under the curve, and when we cranked it out, using all our improper integrals and limits and all that stuff, we found that was infinite. We go, okay, that makes sense. There's infinitely much area under this curve because it goes on for infinity. Sure, that makes sense. Now, this relates to my 1 over n. If you think about this in terms of boxes, this box is 1. this box is 1/2. This box is 1/3. So this is the same as adding 1 over n as n goes from 1 to infinity. So now we know that the summation as n goes from 1 to infinity diverges. And we call this a harmonic series. What if p is bigger? Let's say we look at, oh, you weren't supposed to get everything at once. Oh well. Life's a bitch, then you die. So if p is bigger than 1, like x squared, this goes to 0 much faster, and you still have the square analogy, but you're adding 1 over x squared, so 1 and then 1/4 and then 1/9. And when we did the integral from 1 to infinity, way back when we did improper integrals, of 1 over x squared, we got 1, which I think is way cool. That means the area under this curve is the same as the area in this pink box here. But I digress. So the reason this actually works for p greater than 1 is if you're integrating 1 over infinity of 1 over x to the p, that's the same thing as x to the negative p. And when you integrate that, if you add 1, divide by what you get, if your power of x is all of a sudden bigger than 1, and you end up with your x now on top, when you plug infinity into that, your function blows up, your integral blows up. Whereas if the x is still on the bottom, if you have 1 over infinity, you get 0. So the integral converges. So let's look at some examples, or ask some questions of ourselves. Do the terms go to 0? If not, diverges. Is it geometric with r less than 1? If not, diverges. Is it a polynomial-like rational function? And what's your p? And then it's based on the p-value. And I'll show you what I mean by polynomial-like in a minute. And other functions, you want to think about the speed of the function. Who's faster? If it's fast enough to go to 0, it's fast enough to converge, as long as we're not talking about polynomials. Okay. So let's look at some examples. 1 over n times n plus 3. Okay, this is basically a p-series. I say basically because it's not 1 over n squared, but it's close enough to 1 over n squared. As you get out to infinity, it's really close to 1 over n squared. So we're going to look at this as your p equals 2. 2 is bigger than 1, converges. Let's check this one out. I have 5n squared plus some crap that I don't care about, over n cubed plus some crap I don't care about. This is all I care about right here. I've got 5n squared over n cubed. So comparing the powers, 3 minus 2 gives me a 1. So this is basically a p-series where p equals 1. And we know if p equals 1, diverges. Let's try this one. Okay, so I have 2n plus 5 over 3n minus 2. I have a p-series where now wait a minute, we don't even give a shit that it's a p-series. This theorem, this goes to 2/3. The terms do not go to 0. Diverges like a mother, very fast. So let's try another one. Here's this one. Oh, now this one's kind of funky. So I have this n to the 5th on bottom. That's clear enough to see. Now this is what's in charge on top. This 4n squared, or this n squared is what I care about. And so it's the square root of n squared. So this top degree is basically a 1. So if I've got n equals, or p equals 1 on top and the power on bottom is 5, the difference is 4. So this is basically a p-series with p equal to 4, which means it converges. Looking at something like this, oh, we're not even talking about p-series here. The terms clearly go to 0 because I've got this big old honking exponential on the bottom. Sine of n is just a wuss. It flops between -1 and 1. The 2 to the n will blow it away. This is basically geometric with r equal to 1/2, and also, yeah, it's going to converge. Now, factorials. Tread carefully with factorials because you may look, well, first you may look at that and go, huh? Let's freak out. We want to take a couple steps to figure out what does this really mean. Since I've got factorials on top and on bottom, I need to go a little slower. So let's write this out. N minus 1 factorial over n plus 1 factorial. Okay, so the top is 1 times 2 times yada, 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 up to 2n minus 1. The bottom, 2n plus 1, is 1 times 2 times yada, yada, yada. I'm also getting up to 2n minus 1, but then I get this additional 2n and 2n plus 1. So all of that stuff cancels. And I'm left with 1 over 2n times 2n plus 1. So again, basically a p-series where p equals 2. So this is going to converge. Well, that's what converges up there. Okay. Now, just to throw one more kink in the system, most of the series we've been looking at, the terms have all been positive, or positive at some point on out to infinity. You know, if the first gazillion terms are negative, I don't really care as long as from gazillion on, they're positive. Now, we want to talk about alternating series where you legitimately have this one's positive, this one's negative, this one's positive, this one's negative, it alternates, hence the name. If A sub n is positive, because we want to make sure it's alternating, and the terms are decreasing, it'll converge. All you need it to do is for this to be decreasing. And frankly, well, not frankly, if these terms are positive and the limit is 0, remember the limit of the terms has to be 0, then it's got to be decreasing. So if you know that it's alternating and the terms are going to 0, then you're good to go. You know it converges. So how does that screw with the alternating, with the harmonic or with the P series? That means with the P series, all I care about is that the P is positive. 1 over n alternating converges. The terms go to 0, we're alternating, converges. This is known as the alternating harmonic series because it's a harmonic series that alternates. Mathematicians are not very creative sometimes. Okay, I shouldn't wax philosophic because I'm already at 16 minutes and they said 16 minutes was too long. So looking at this one, I have alternating my P. Here's a n squared on top and n cubed on bottom. My P is 1, so this will converge. Let's see. Do I have a summary? Quick summary. Oh, good. Almost. Do the terms go to 0? That's the first question you want to ask yourself. Do the terms go to 0? If they don't, the sequence series diverges. Stop, go home, have a beer. Okay. If they do go to 0, then you need to keep going. So now, I'm assuming that the terms go to 0 at this point. So you may think I'm missing some things, but I'm really not. If the terms go to 0, that means if you had a geometric, your R was already less than 1, so you know it converges. Let me go through this. Okay. Mixed functions, we've got crap on top and crap on bottom. The one who goes the fastest is the one in charge on both the top and on the bottom. See, so if you've got 2n plus 5 plus x squared, n squared, it's the 2 to the n that matters on top. And the other stuff is just noise. So let's look at what we have. So assuming you figure out who's in charge on top and bottom. Okay, polynomial-like, and they're alternating. If P is 0, then it diverges. If it's polynomial-like and it's not alternating and your P is less than 1, it diverges. Otherwise, it converges. Let that sink in. So the only thing you really need to stress out about is looking at those polynomial things. If you've got polynomials, you want to figure out what the P is and whether it's alternating or not alternating. Otherwise, if you've got 2 to the n's and you've got factorials that don't cancel, as long as the terms went to 0, then this thing's going to converge. So remember that. Don't make this harder than it is. So hopefully this isn't too long. It's already up to 18 minutes, so I will stop now. If you need more practice problems, just let me know. As always, you know my text number, my phone number.